This is lesson number 22, entitled Number Theory. You might say, what is number theory? Well, to date, we have looked at mostly arithmetic kind of problems. We've added, subtracted, multiplied, divided, raised to powers, taken square roots, all kinds of exciting things such as that. And for many people, that's what they think mathematicians do. They sit around all day, adding, subtracting, multiplying, dividing, taking square roots, maybe solving equations. That's not what mathematicians do. Most mathematicians are involved in looking at structures, how things work, why things work. Can we generalize? And number theory looks at arithmetic and tries to get to the underlying truths about what's happening, how arithmetic works. And we're going to just take a very basic look at some things and learn some of the things that were developed by ancient mathematicians as they began their struggle to truly understand this thing we call arithmetic. First, we need to learn some terminology. The first term is factor. What is a factor? Well, a factor is a number that divides in evenly. And here we see the factors of 36. These are the only numbers that divide evenly into the number 36. When I say divide evenly, it means they divide without a remainder. 1, 2, 3, 4, 6, 9, 12, 18, and 36. All other numbers, if you try to divide them into 36, you would get a remainder. So these are the factors of 36. So one could say, is 8 a factor of 50? And the answer is no. 8 is not a factor of 50 because if you divided 8 into 50, you would get a remainder. In fact, you would get a remainder of 2. What the remainder is irrelevant. Unless the remainder is 0, you do not have a factor. The other word that is usually coupled with factor is multiple. Here we see the multiples of 36. A multiple is a number obtained by multiplying the number in question. So these are numbers that are obtained by multiplying 36. 36 times 1 is 36. 36 times 2 is 72. 36 times 3 is 108. 36 times 4 is 144. ... means forever and ever. How many multiples of 36 are there? An infinite number. How many factors of 36 were there? A very few. So factors are limited, multiples are unlimited. And of course, since 72 is a multiple of 36, then 36 is a factor of 72. And we're going to take a look at some things leading us, for example, to find a way to find the lowest common denominator, something we talked about in earlier lessons on fractions. So, let's see. If 8 is a factor of 24, that means that 8 divides evenly. And as you can see, 8 goes into 24 3 times with a remainder of 0. 3 times 8 is 24. 8 is a factor of 24. 24 is a multiple of 8. And the ancients, as they were looking around at the various counting numbers, saw something quite significant. There were really 3 types of numbers. And you'll notice on your screen, you see the first 20 of the counting numbers. You'll notice that 1 is the only one of those numbers colored in green. And there's a reason for that. The ancient mathematicians of Egypt recognized that 1 was the creator number. All numbers have 1 as a factor. 1 has only one factor. In fact, it is the only number that has only one factor. And when I'm talking about numbers here, I'm talking about counting numbers. So 1 is very, very special. And it's colored green because it's the only one just like it. The other numbers, you'll notice, are colored in 2 different colors. The numbers colored in red became very important to the ancient mathematicians because those were numbers that could only be factored one way. They only had 2 factors. 1, since all numbers have 1 as a factor, and the number itself. The only way to get 2, 1 times 2. The only way to get 3, 1 times 3. The only way to get 5, 1 times 5. In fact, if you think back to the first lesson, we looked at the physical representation of multiplication as rectangular arrays of numbers. These numbers could only be shown in one way, 1 times itself. All other numbers, other than 1 and these numbers that we see colored in red, can be shown to be rectangular arrays of at least 2 different types. For example, 10. You notice 10 is not red on your screen. 10 can be 1 times 10 or 2 times 5. The ancients believed that these numbers, the ones that could only be obtained by multiplying 1 by the number itself, there's no other multiplication array that would work, were very significant. And they called these numbers prime, P-R-I-M-E, prime numbers. And the prime numbers came to be very, very important. The other numbers, numbers that were not prime, that could be divided by 1 and themselves, as well as at least one other number, were called composite. So we have basically 3 types of numbers. We have 1 all by itself, we have primes, and we have composites. It's very interesting to note that in ancient times, quite frankly, when men were more important than women, at least of course the men ruled, it certainly isn't true today, hopefully, but the fact is that men decided that men's names were important and women's names were not important. And you'll notice that the prime numbers that we saw on the screen included only odd numbers except for the number 2, since all even numbers other than 2 are divisible by 2 and therefore have a factor other than 1 in themselves. So all even numbers except for 2 are composite. And since the rest of the prime numbers are odd, men decided that they would give their sons names that had an odd number of letters, and women were given names with an even number of letters. And for example, giving one's boy child a name that had an even number of letters would be like, in the United States, naming a boy, Marcia Sue. Obviously, he would get into a lot of fights. So again, this is not from experience. I wasn't living back in ancient Egypt. But the fact is, this is what I've read and heard, and in their world, the prime numbers were considered very, very important. You must understand that most of these mathematicians looked at mathematics as a religion, an explanation of their being, an explanation of their universe. So let's continue in our look at number theory and use these prime numbers to get at some very important circumstances. We're going to factor with prime numbers, which is called prime factorization. On your screen, you see the prime factorization of 36. The way we prime factor a number is to simply start with the number 2. Does 2 divide the number in question? If it does, we write the 2 down with a little branch sticking out of the number, as you see here, a little branch coming out of the 36. And then we write down in the other branch, to the right of the 2, what the other factor is. 2 times what is the number? In this case, 2 times 18 is 36. And then we ask ourselves again, does 2 divide the new number? And the answer here is yes. 2 times 9. Does 2 divide 9? No, it doesn't. The next prime number is 3. Does 3 divide 9? Yes, it does. 3 times 3, and now the remaining number 3 we know is prime. And therefore, 36 can be prime factored into 2 times 2 times 3 times 3. Or if you'd like, using exponents, 36 is 2 squared times 3 squared. Now, this is the only possible product of primes. Product is a multiplication answer, and we know what a prime number is. There is no other way to get 36 through multiplying primes than 2 times 2 times 3 times 3. It is unique. And in fact, it was discovered that every single composite number has a unique product of primes. Well, here are 3 composite numbers: 84, 105, 111. What I'd like you to do is, using the list of primes, if you need to, go back to that graphic that lists the prime numbers between 1 and 20, and use that to prime factor 84, 105, 111. And when you're finished, come on back to the tape, and we'll work it on the screen. Okay, 2 divides 84, 2 times 42. 2 divides 42, 2 times 21. 2 does not divide 21, but 3 does. 3 times 7, and since 7 is prime, we have completed our factor tree. We completed our prime factorization of 84. 105 cannot be divided by 2. It can be divided by 3. And remember, we know that from our knowledge that 1 plus 0 plus 5 is 6. And since the sum of the digits equals 6, 105 is divisible by 3. 3 times 35 is 105. 35 cannot be divided by 3, but it can be divided by 5. It ends in 5. And 5 times 7 is 35, 7 being prime. Our factorization of 105 is complete. 111 is also divisible by 3. It is not divisible by 2 since it's an odd number. 3 goes into 111 37 times. Now, if you tried 2, I couldn't do 2, 3, 5, 7, 11, etc., all the prime numbers between 1 and 20, none of them would divide 37, which means what? It means that 37 itself is a prime number, and the prime factorization of 111 is 3 times 37. So now we see the product of primes for our 3 numbers. 84 is 2 squared times 3 times 7. 105 is 3 times 5 times 7. 111 is 3 times 37. You'll notice that those 3 numbers each had a factor of 3. That is, they had a common factor. One of the things we investigate in number theory is, given 2 or more numbers, what is the greatest common factor, the GCF, the largest number that divides each of the numbers in question. How would we do that? Well, obviously we're going to use prime factorization. Let's take a look at a problem. We want to find the GCF of 84, 72, and 132, and we want to do it in a way that we can conclude the answer is correct, a very ordered method of doing this. The first thing we do is we prime factor each of the numbers. And you'll notice the prime factorization of 84 is 2 times 2 times 3 times 7. We already did that previously. The prime factorization of 72 is 2 times 2 times 2 times 3 times 3. And 132 can be prime factored into 2 times 2 times 3 times 11. Then I go back and I circle any time there's a prime in each of the prime factorizations that is common. So you'll notice I've circled 2 2's in each of the factor trees. You'll notice in the factor tree for 72 there is a third 2. That third 2 is not circled. And the reason is, well, there's no other place where there's a third 2. Each of the factor trees, in this case all 3, must be able to be circled. So we have 2 2's circled in each factor tree. We've also circled a 3 in each factor tree. Notice we haven't circled the second 3 in the factor tree for 72. Nor have we circled the 7 in 84's tree or the 11 in that of 132, because these are not common factors. So our greatest common factor is the product of the common factors. That is, if a number is divided by 2 and can be divided by 2 again and can be divided by 3, it can be divided by 12. So 84, 72, and 132 have a GCF, a greatest common factor of 12. Let's see what that means. On this next graphic, you can see that we have the numbers 84, 72, and 132 written as the product of 12 times another number. 12 times 7 is 84. 12 times 6 is 72. 12 times 11 is 132. Those numbers that are multiplied by 12, you'll notice, are the product of the remaining primes in the factor tree of the individual number. 7, of course, is 7. 6 was the missing 3 and the missing 2, the 3 and 2 that were not circled. And, of course, 11 was not circled in the factor tree of 132. So we could see that there is no common factor for the other numbers, for the 7, 6, and 11, other than 1. And therefore, the GCF, the greatest number that divides both 84, 72, and 132 is 12. Let's take a look at the next three numbers, 38, 95, and 171. We have prime factored those numbers. The only common factor is 19. If it's the only common factor on the factor tree, then guess what? It is the greatest common factor. The GCF is 19. So 38 would be 19 times 2, 95 would be 19 times 5, and 171 would be 19 times 9. GCF of 19. The next series of numbers gives us a third circumstance. In the first circumstance, we actually had to multiply the primes. In the second circumstance, when we just looked at, we only had one common prime factor. That was the GCF. Here, for 44, 27, and 175, we have no common factors. Nothing is circled. In fact, there isn't even a number common anyplace. I mean, the fact is that there are no 2s or 11s any place other than 44. There are no 3s except for 27. We don't care about that. The fact is we care the fact that there is no common factor. There's no factor that appears in each of the three trees. And therefore you might be thinking, well, there is no common factor. Yes, there is. Remember, every number can be divided by 1. 1 is the creator number, if you will. And therefore, the GCF, the greatest common factor for 44, 27, and 175 is 1. And we have a word, or actually two words for that. If numbers, two or more numbers, have a GCF of 1, they are called relatively prime. And later on in mathematics, well beyond the scope of this course, the notion of relative prime is very important. It gives us some clues as to how things work. But right now, it's a set of words. It simply means that the GCF is 1, then the numbers are relatively prime. Now remember I said we could use number theory to be able to find the lowest common denominator. Remember, in finding the common denominator, we multiplied. So what we need to find is the least common multiple of a set of numbers, the LCM, the smallest, least number that is a multiple of the numbers in question, of two or more numbers. In our first problem, we have three numbers for which we want to get the LCM, 45, 54, and 50. We start with the prime number 2, and we look at each of the factor trees and find the factor tree that has the largest number of 2's in it. Well, you'll notice there's no 2's in 45, and 54 and 50 each only have 1 2. So I circle one of those 2's. In other words, we'll need a 2. Then, as we see in the next graphic, after I circled the 2 in 50, I went looking for the most 3's that were available. And there were 2 3's in 45, but there are 3 3's in 54. So the most 3's I need is 3 3's. I circle those in 54. How about 5? Well, there's a 5 in 45. There's no 5 in 54. There are 2 5's in 50. So I circle both those 5's. The maximum number of 5's I need is 2 5's. There are no other prime numbers left. There's no 7's or 11's or anything beyond that. So in order to find a number that can be divided by 45, 54, and 50, that is, a multiple of these three numbers can be divided without remainder by all three numbers, I must multiply all the circled numbers. The LCM is 2 times 3 times 3 times 3, the 3 3's, times 5 times 5, the 2 5's. When you multiply that out, you get 1,350. As we can see, 1,350 can be obtained by multiplying each of the numbers in question by a whole number. 45 times 30 is 1,350. 54 times 25 is 1,350. And 50 times 27 is 1,350. 1,350 is the smallest number that can be obtained by multiplying 45, by multiplying 54, by multiplying 50 by some whole number. It is the least common multiple of those three. Now we can do both GCFs and LCMs for 2 numbers. We've done it for 3 numbers. Actually do it for as many numbers as you like. The process remains the same. Let's look at our next problem. We have 44, 27, and 175. We'd like to find the GCF and the LCM. We notice as we look at our factorization, our little tree diagram with the prime factors, we notice that there is no common factor. There is a 2 in one of the trees. There are 3s in the other tree, and 5 and 7, but there's no common factor at all. And therefore the GCF must be 1. Now an interesting happens when the GCF is 1. Because now to find the LCM, you'll notice that we circle the 2 2s in 44. Notice there are no other 2s. We circle the 3 3s in 27, and there are no other 3s. We circle the 2 5s in 175, the 7 in 175, and the 11, I got tired of using circles, so we have a little box around, a little square around 11. And in effect, we've circled all the numbers. And the LCM is simply 2 times 2 times 3 times 3 times 3 times 5 times 5 times 7 times 11. 207,900. Since there are no common factors in any of the numbers, the actual LCM is the product of the 3 numbers. 44 times 27 times 175 is 207,900. The LCM, the least common multiple of those 3 numbers. Okay, so we've seen how to do the GCF and the LCM, and the LCM can be used to find the lowest common denominator. If I had 2 common denominators that weren't quite so simple to look at, for example, let's say I had 45ths and 30ths, and I wanted to find the common denominator, the lowest common denominator, to add a bunch of 45ths and a bunch of 30ths. What I would need to do is find the least common multiple of 45 and 30. And the least common multiple of 45 and 30, which happens to be 90, would be the lowest common denominator. That's a lot smaller than multiplying 45 times 30 to get the common denominator. So again, the whole idea of this number theory is to find the structure of the numbers we're working with and use that knowledge of the structure to enable us to operate, to add, subtract, multiply, and divide, etc., with greater ease. Now you may be asking the question, how did they find the prime numbers? I mean, did they pray one night and out of the blue somebody came down from the mountaintop and said, here are the first 100 prime numbers? That's not how they did it. Obviously 1, 2, 3 were easy to find. Of course 1 is not a prime number, a very special number. But the question now came about, how do you find prime numbers? Well, that question was answered thousands of years ago by a gentleman named Eratosthenes. Eratosthenes lived way back in the BC times. And Eratosthenes did a number of interesting things. He was I believe, the first person to measure the circumference of the earth. Never having been very far from where he lived, he used the shadows and wells. It's a long story. You can read about it if you want it in the history of mathematics. But he actually measured the circumference of the earth very accurately. That's very interesting when people talk about that Christopher Columbus was fighting all these people who thought the earth was flat. They knew the earth was round in ancient times. It was the ignorant people in Christopher Columbus's time who did not know that the earth was round. Well, Eratosthenes, besides discovering the circumference of the earth fairly accurately, was able to come up with a method of finding prime numbers. And to this day, this method is in many textbooks. It's called the sieve of Eratosthenes. A sieve is something used to filter material through. And by filtering the numbers through the sieve of Eratosthenes, we realize is we get the prime numbers. On the whiteboard here, you have the first 50 counting numbers. Now you must excuse me. I am one of those people who needs lines to write straight. So unfortunately, I believe on your screen the numbers are rising a bit as they go from left to right, but that's okay. You can see the numbers are lined up by their ones place values. Okay? We have 1, 11, 21, 31, and 41 all lined up one under the other. So 1 is a very special number. Let's go ahead and, well, let's just erase it. We'll erase the 1. Now we're left with numbers that are either prime or composite. The first number is 2. Now we know that any number that can be divided by 2 is not prime, is composite. What can we do? Well, we can simply mark all the numbers that are divisible by 2. Rather than taking the time to do that, let's just notice that these are numbers that are lined up with 2's in the ones place, 4's, 6's, 8's, and 0's, all the even numbers. Let's go ahead and just simply erase those. But we won't erase the 2. Why not? Because the 2 is prime. And now we're going to look at the 3's. And we start with 3, and we know that all the numbers that can be divided by 3 must be composite. Now, do those numbers have any endings like even numbers? No, they don't. The numbers that can be divided by 3 are every 3 numbers. Well, and those even numbers are gone. The 6 and the 12 and the 18 are gone. So we have 9 and 15 and 21 and 27 and 33 and 39 and 45 are gone. The next number is 5, the next prime number. And let's just erase all the numbers that end in 5 or 0. Well, the numbers that end in 0 are already gone. So we erase these numbers that end in 5. And now we have 7 left. And 7, well, 14, 21, 28, 35 are gone. 42 is gone, 49. And guess what? What you have left on your screen, other than the dust from the markers, are the prime numbers up to 47. That is the prime numbers less than 50. That is how Eratosthenes found the prime numbers, and that is how we can find the prime numbers. And in fact, we've now sort of concluded our very basic look at number theory. We've looked at the notion of multiple and factor. We've discovered what prime and composite numbers are. We've looked at how to find the greatest common factor and the lowest common multiple. The lowest common multiple is useful in finding the least common denominator. And we've looked at the sieve of Eratosthenes to see how we find prime numbers. In the next lesson, lesson number 23, we will look at number patterns and discover more interesting facts about our friends, the arithmetic numbers. See you there.